So, today we're diving into what feels like a real pivot point in medical AI. We've seen models that can read an X-ray for a while now.
For a while, yeah. But this is different.
This is very different. On January 13th, 2026, Google Research released something that, well, it fundamentally changes the geometry of the problem.
Literally changes the geometry. We're talking about moving from flat 2D snapshots to full 3D volumetric understanding.
Exactly. We're looking at two new open models today. There's
Okay.
MedGemma 1.5 for the images and text, and MedASR for speech.
Right.
And the mission for this deep dive is, I think, pretty clear. How do you get an AI to see inside a body in 3 dimensions and hear complex medical jargon, all without needing a giant server farm to run it?
And that last part is the kicker, the offline capability. That's the game changer.
Okay, let's start with the visual side then, MedGemma 1.5. The big leap from the last version seems to be this ability to ingest high-dimensional volumes.
It is. We're talking CT scans, MRIs, even whole slide histopathology.
So we're not just looking at a photo of a lung anymore, we're looking through it.
Precisely. Think about how a radiologist actually works. They don't just look at one slice of a CT scan.
No, they scroll through the whole...
Yeah, scroll through the whole volume, to understand the shape and extent of a tumor or an issue. MedGemma is now doing that kind of analysis across the entire volume.
And the performance jump is pretty significant. I saw they clocked a 14% improvement in classifying disease-related findings in MRIs.
Which is great, but what really jumped out at me was the longitudinal stuff, the time travel aspect, as you called it before we started.
Right, for tracking disease progression.
It's vital. The model can now look at a series of chest x-rays taken over months and spot what's changed. It got a 5% accuracy boost there.
Which is good, but the next number is the one that really caught my eye.
The localization.
A 35% improvement in its ability to pinpoint exactly where the problem is?
Yeah.
That's huge.
It's the difference between there might be an issue here and the issue is right here.
But here's the thing that I think might confuse some people. It's a 4B model. 4 billion parameters. In today's world of 100 billion parameter models, that sounds, well, it sounds tiny. We usually think smaller means less capable.
And in this context, that's not the case. Here, smaller means specialized and efficient.
Okay.
By keeping it at 4B, they've made a model that can run on local hardware. You don't need to send that sensitive patient MRI data up to the cloud.
Which is a massive privacy and security hurdle for hospitals. Just gone.
Exactly.
So we have a model that can see better. But so much of medical data isn't pixels. It's a doctor dictating notes. That brings us to MedASR.
The other half of the puzzle. General speech models, even the really, really good ones, they just stumble over medical vernacular.
You mumble a complex drug name and it hears something completely different.
It hallucinates a common word that sounds similar, yeah. And the stakes are obviously a bit higher than getting your grocery list wrong.
I saw they benchmarked MedASR against Whisper Large V3, which is, pretty much the industry standard.
And the gap was enormous. On medical dictation tasks, MedASR had 82% fewer errors.
82%. That's not just a marginal gain.
No, that's the difference between a tool that's helpful and a tool that's a liability. It allows a doctor to speak naturally, use all the acronyms and jargon.
And the model just gets it. And can even use that text to prompt MedGemma to look at the scan.
Now you're connecting the whole workflow, the verbal to the visual.
And this isn't all just theoretical. I was glad to see they included some real-world deployments. In Malaysia and Taiwan,
the Malaysian example from MedASR is a perfect use case. They built an interface, Ask CCG.
Right.
It ingested over 150 clinical practice guidelines. So a doctor can just ask a question instead of flipping through a huge PDF manual to get decision support.
And in Taiwan, the National Health Insurance Administration used it for data extraction from, 30,000 pathology reports?
30,000. To evaluate preoperative assessments for lung cancer surgery, that's just a massive unstructured data problem that it helped solve.
It really shows that this foundation model approach is working. They aren't trying to ship a robo-doctor.
No, they're releasing the clay. They're releasing MedGemma and MedASR and letting developers, hospitals, and researchers be the sculptors.
They're even putting money behind it with that $100,000 Kaggle challenge. But we should be really clear. For anyone listening, you don't just download this and let it start making diagnoses.
Oh, absolutely not. No, these are tools for validation, for assistance. They are powerful, but they are still just tools that have to be validated in every specific use case.
Okay, so that leads me to my final thought for you to take away. If these models are now small enough to run offline on, say, a rugged laptop,
right,
but also smart enough to read 3D MRIs and understand a specialist's dictation, how close are we really to deploying this kind of expert-level diagnostic assistant in a remote clinic with no internet connection at all?
The technological gap is closing fast. I think now it's just becoming an implementation gap.
Thanks for diving in with us.